Why does water on Earth look so different? That's what we're going to talk about today. Hi, this is Jill from the North Woods, talking about nature right outside our front door. Last time we were talking about stars and planets and how they look like different colors. I was thinking, is that outside our front door? But we see stars with different colors. We see planets with different colors. Mars does look red, so it's kind of outside our front door. But this time, we're wondering questions like, why are some lakes deep blue? Why is the Caribbean turquoise? Why is Lake Superior almost black at times? And we wonder what makes these different colors. This enormous variety of colors that water can be. And even sometimes it can change. A lake during the morning will look different when it gets stormy out later in the day. And then there's places like Iceland. I went to Iceland and you see that stunning blue glacier, or the Canadian Rockies, Moraine Lake. There's different places where these glaciers, instead of being white or clear, are this stunning opaque turquoise, almost like it was painted that color. I wouldn't have believed it, except I saw it myself, although the pictures get enhanced a little bit. But essentially, if you look at a little pond, hour by hour, the color of the pond will change colors. The tropical lagoon over white sands can almost appear to be like a mint green. Glacier ice, when inside of a cave or crevasse, goes to a deep luminous blue that almost like it glows from within. But water is water. The chemical formula of water, H2O, in the Caribbean is the same H2O that's in Iceland or in Lake Superior. And so why does it look completely different? And we've been exploring in this series about how color happens and how it's absorbed. It relates a little bit to the feather discussion. Some colors are because something is that color. Like if you look at a cardinal is red. Their feathers are red. But if you look at a blue jay, the blue jay actually has colors coming from the way that its feathers absorbs and reflects the light. So it's the same kind of interesting way when we look at light in the world around us and color in the world around us. And we talked about spectrometry. That's the science, basically, of reading what light tells us. And so now we're going to bring it back, like I said, back down to earth and look at the basics of what is going on. So if you look at pure water, just regular water, no particles, algae, sediment in it, why is it blue at all? And that is because the water molecules absorb light selectively. So essentially, they absorb light at the red ends of the spectrum more readily than the light at the blue ends. And that means it has to do with the hydrogen and the oxygen atoms in the water itself and the way it vibrates. We're not going to get too deep into that. But essentially, the frequencies it resonates at match those of red and infrared wavelengths. So it absorbs that energy as the light goes through it. So when sunlight enters water and travels deeper, the reds disappear first because they're being absorbed. Just like when we talked about how atmospheres and planets absorb light, our water is absorbing light. So the green, so the red disappears first, the orange and yellow start to fade next, green eventually weakens, and blue and violet penetrate the deepest. They're the last standing color when we're looking at it. So the remaining blue light gets scattered, so it scatters throughout the water molecules, and that's what we see. The water isn't reflecting the blue sky. It's primarily, at least not primarily, it does reflect the blue sky a little bit, but it's filtering out everything else. So when you look at the color of water, just like when you look at the colors of many of the things that pass through gas, what you're seeing is what's left. The colors that do not get absorbed by whatever it is passing through. It's filtering out everything else, giving us back blue light, and blue is what survives the journey. If you look at a glass of water and you look through it, it is barely detectable. Large volumes of it, though, lakes, oceans, deep fjords, the filtering becomes visible. The water becomes intrinsically blue because of the light it's absorbing. It's subtle enough that we need depth We need a lot of water in order to see it. The violet wavelengths are technically even shorter than the blue, and they penetrate even deeper. But our eyes are very sensitive to blue and not very sensitive to violet. So blue is what we see. So it's a combination of what the water chemical makeup is absorbing, but also what our eyes are better at seeing. There's other animals out there in the world that see violet a lot better than we do. So it might look a little bit different to them. If we look, towards the ocean, far from shore, away from any sort of river runoff, because that can change the nature of the way that an ocean will look, away from nutrient blooms or where it's not shallow, where we see other colors, at the bottom of the ocean, the water is remarkably pure there. And it is so pure, the deep water then select the absorption. But then that deep water, you have a selective absorption plays out fully. The red is gone. By 30 feet, redfish appear nearly black because there's no red light left to illuminate them. By 30 meters, 40 meters, the salt water, almost every wavelength except for blue, has been absorbed. And what remains is this very saturated navy that you see in photographs. The open Pacific, the open Atlantic. Think about Lake Superior. That's one of the largest freshwater lakes in the world. It's deep, it's cold, it's relatively clear. You get away from the shoreline and the mouth of rivers, it's remarkable that a small inland ocean, essentially, it behaves remarkably like a small inland ocean, although it's not because it's fresh water. The water is clean enough that the light penetrates deep, long wavelengths and the color gets absorbed fully. And what scatters back is predominantly blue. On a calm, sunny day, nothing stirring up sediment, nothing creating wave caps on there. Lake Superior can almost be impossibly blue. I mean, it's just one of those, I don't know, like I said, I grew up on Lake Superior. I have seen Lake Superior in many different circumstances, and it's stunning that it can go from this black blue to this very true blue. And it's that kind of clarity is because of two different reasons. Like I said, the more you have of depth and the more you have of cleanness of the water, you're really taking on that water's own chemistry and showing you its true colors. But if we look at tropical waters, you've seen those pictures of the Caribbean with that gorgeous, gorgeous blue. There's, you almost get like a brilliant turquoise. It's bright and clear. It almost glows blue. And the mechanism is a combination of two different things. Is that first of all, the tropical water is shallow enough that the bottom is clear, so you can actually fully see down to the bottom. The shallow light reaches the bottom, and then instead of being fully absorbed on its way down, the bottom is very pale, usually white sands or light-colored corals, calcium carbonate sediment at the bottom. It starts to reflect light back up again. And when the light reflects back up through the water on its way to our eyes, it passes through a few feet of water. The wavelengths get knocked out. We know that. And what comes back to us is a mix of that blue scattered water itself, but also you're getting some blue-green in there too. The shallower water, the more reflective bottom, the brightness coming in there, that's going to give us, instead of having that navy blue take over, we're going to start to see a lighter blue. And the water's own blue absorption starts to dominate. So if you've ever snorkeled over like a shallow reef, swim out to the bottom and where the bottom drops away, you'll start feeling that color shift from bright turquoise blue back to that dark blue again as the floor disappears beneath you. So you're no longer getting that reflected light from the shallow shores. One of the most dramatic blues, and if you've ever seen it, you'll know for sure, is when you see those glaciers. So now you have a type of water that operates with a different kind of mechanism and provides some of the most astonishing blues and turquoise in the natural world. You've probably seen various places where there are glaciers, Canadian Rockies, Moraine Lake, but the glacial lakes and glaciers in Iceland. Like I said, I went to Iceland. I drove the ring road, and my brother and I took a tour in a cave, and it had that glowy blue glacier color to it. That color is impossibly bright, opaque, and sort of a milky turquoise. And it doesn't come from the depths like, the ocean. It comes from artificial, and it almost looks artificial because it shouldn't be possible for water to be that saturated. The secret ingredient is something called glacial flour. And when, not flour like you're going to bake bread flour. And when a glacier moves, it grinds, it slowly goes under pressure, and the ice drags itself over bedrock beneath it, pulverizes the rock around it into this fine particle till they're smaller than silt, just very small particles of it, almost powder. And as it gets ground up, these few micrometers across, that powder, that glacial flour, sometimes called rock flour as well, gets carried away by the meltwater into the lakes and the rivers. And because these particles are so tiny and so light, they don't sink. They stay suspended in the water, sometimes for months, and creates what's called glacial milk. Now, my brother and I did get a chance to go over towards a glacier. And one of the things you'll notice in the pool of water, it was like a little lake, and then the glaciers were above it. The water gets a very milky white. It's really a weird color, like a gray, milky color, cloudy, opaque. And that is because those particles are suspended in the water, not sinking like usually particles sink to the bottom, instead floating there. So it's a bit of optical magic. And that suspended particles scatter the light because of their size. It's just that tiny, tiny size they have. And they preferentially scatter the shorter wavelengths. So the blue and the green bounce off of them intensely, scatter in all directions back towards your eyes. And the longer the wavelengths, red, orange, get absorbed by the water as usual. And the results then will turn into this brilliant, bright neon turquoise that you're seeing. And it's not the bottom that's reflecting through the water. It is the little particles that are suspended and gives you sort of that blue-green color. Like I said, in my case, the colors almost looked milky gray. And it just depends on the makeup. You're getting in Iceland ash as compared to other places where you're not going to have ash in that suspension, but the principles are the same. The concentration of this glacial flour changes with every season. So springs, when the glaciers start to melt, these areas can look almost ordinary. But by midsummer, the glacial melt is at its peak, and maximum glacial flour is flowing into the lake. The lakes are melting and the water's coming down. That's when the color can get more intense. And so you can watch time-lapse videos of some of these lakes across the years and see them change different colors. I stood next to, like I said, the Icelandic glacial river once, and the water coming out of it was this very weird metallic silver blue, like I said, almost milky white. It's been grounding those glaciers for thousands of years, and a lot of it ash and volcanic, and it's now suspended in the meltwater. And you just have never seen anything quite like it. Like I said, I went to Iceland. I've never seen so many things where I go, well, I've never seen that before. You just don't know the science behind them, but it can change. I have seen other types of glacial lakes when I've gone to Rocky Mountain National Park. So the real question, I think, comes in then when we look at the glacial lakes is, why do the glaciers themselves, that glacier ice, look at times white? So they're not clear like you would see ice and it would be see-through. It's typically because the surface is jagged and weathered, full of cracks, and those disrupted surfaces scatter wavelengths of light equally, and it scatters all colors of light. So it ends up looking very white. But if you go into a cave or a crevasse and standing there facing it where the fresh ice has just broken away, that's where you're going to suddenly get surrounded by that deep, glowy blue. The undisturbed ice on every side you see is electric blue. It radiates almost from within. And like I said, we took a cave tour and we got to see that. Snow, then, if you think about it this way, snow falls on a glacier year after year. Each new layer buries the previous year. and compresses, squishes underneath that weight. And over decades, that pressure squeezes out all the air bubbles out of the snow, out of the water that's there, and gives that ice its white, its scattered appearance. But then the ice crystals grow larger, more packed more densely, and then this dense bubble-free ice essentially is a thick slab of pure water. And it's thick, it's pure, and absorbs all the red, right? We know that. Transmits all the blue, and the longer path of light travels through the ice, the more the red gets absorbed, the more that the blue emits from that item. And so those deep, old glacier ice gets very intense blue. So it's a source of why we see some of those glaciers, that some of them look white, weathered, and that has to do with the air and the jagged nature of it. But the interior ones glow blue because they have centuries to work out all their jaggedness, all their air bubbles in it without interruption. So it's kind of the same physics as when you're talking about an ocean. The physics in the glacial lakes just operate inside of solid ice that's been compressed hundreds of thousands of years. But now let's bring it all the way home, maybe a little closer to home. Think of a small pond. Some small ponds are very shallow. They don't have a lot of depth. The water itself has its own chemistry. They're dominated by colors, far more in the chemistry than a lake or an ocean is, because it's full of organic matter, decomposing plant matter, algae, sediment. It muddles the absorption. And so mostly what you're seeing when you're looking at a pond is not the intrinsic color of water. You're seeing a reflection of the sky itself. A calm pond acts almost nearly as a perfect mirror to the blue sky above. But a gray cloud can mean that the water turns gray. A sunset with an orange sky and pink will turn the water a similar color. And so it's not because the water itself has changed, but the pond is actually just showing what's above it. The wind changes things too. When the wind picks up and roughens the surface, it breaks up that mirror into thousands of small facing mirrors in every direction. So instead of getting a clear reflection, the light is scattered in all different angles all over the place. That water darkens. The colors become less defined. Even if you see some algae blooms, that introduces a whole other set of colors. Chlorophyll absorbs red and blue light and reflects green, which is why the pond thick with algae turns green regardless of what the sky is doing. Dissolved organic material from decaying leaves can tint the water amber or tea-colored. I was at a marsh last weekend, and if you ever look into this river that's below it, there's so much decaying material falling into this marsh river that the water itself is it looks like tea. It looks like a very dark tea. So you'll see different colors. So then the small pond, the small river can shift between blue, gray, green, gold, dark space in the afternoon. And each change is a message about the sky, the wind, what's growing in the pond, what's decomposing in the pond. And if you watch a familiar pond across seasons, you'll be able to read what's going on. As soon as I see that tea color in that river, I know a lot of materials from last winter is now decaying inside of that river. If you ever notice, too, that if you see whitecaps, this is a phenomenon that we see on, like Lake Superior, on oceans, even some bigger lakes. A calm blue ocean is, very nice and blue. Blue scatters back up to us, but then the wind picks up. The waves begin to break. The crests turn white as its turbulent seas are forming into these waves. And the more white there is, until like a full gale wind, it can look very pale. The blue is replaced by churning, foaming, white water. The water itself isn't changing color, its physics is changing. When the waves break, they are trapping like millions of tiny little air bubbles in them. And those air bubbles are much larger than the water molecules. And so it's doing another selective absorption, large enough that it scatters all the wavelengths because of the rough water. And so the orange, the green, the yellow, the blue, all scattered. And that's where you start producing white caps. I'm going camping in a place called Whitewater. Same idea, but it's the same reason that the clouds are white. Clouds are made of tiny little droplets, and those droplets are large enough that they scatter all the colors equally and that the whole spectrum comes back to you, and what you see is white or some shade of gray. A white cap is essentially, a similar thing of a cloud formed inside the water itself. The bubbles cause the same equal wavelengths to scatter everywhere because of the air. So when we see a sea that is calm and deep, you're seeing the water's own chemistry. When it's rough, you're seeing the light bouncing off all the air bubbles inside of it. If you ever get a chance to see polar seas, sometimes they will look black. The oceans are surprisingly dark or deep navy or, like I said, black itself. And part of that has to do with the geometry. The sun is low on the horizon because the poles are on top and the sun's somewhere in the middle. But it basically is at a low angle. The light gets more reflected off of the surface. And rather than entering in the water and scattering, it's less penetrated by light. Less blue gets scattered back out. And so the water just looks darker. In calm conditions, that dark water becomes mirror-like, almost like like polished obsidian, that kind of thing. And that's the reason that polar exploration, the photography is so striking. The geometry of the light in those latitudes does, interesting things to the way that the colors work. And maybe, too, you've even heard of some places where there are pink lakes. There are bright pink lakes. It's like bubblegum pink, flamingos, that kind of color. And the shade is applied. You look at it as a photograph and you think it looks fake. But what this happens is when you get extremely salty water, maybe lakes with salt concentrations from the bed itself, those conditions centralize these microorganisms that thrive nowhere else. This algae is a very specific kind of algae strain, and certain kinds of bacteria strain produces red and pink pigments, and in the form of UV protection. So essentially, the sunscreen pigment that the organism manufactures to survive in these intense light, shallow areas are highly reflective water. And so these organisms grow, they color the whole lake. And so you've seen some examples, Lake Hillier in Western Australia. There's Lake Retba in Senegal. I mean, you've probably seen pictures of them. If not, Google some of these pictures of pink lakes. But they come from biology and not from chemistry. It's the living objects inside of the lake and not selective absorption. Sometimes, too, if you ever had a chance to go in and see a sea cave or underground rivers, in those particular systems, the water can almost glow an intense electric blue again. When the light enters through a narrow opening, what you're seeing is that same physics that you see with the ocean. It's concentrated, clear, pure water confined to a space. The red gets absorbed, the blue survives and scatters, and when a single beam of light enters the cave and hits that clear water, the blue scatters in all directions, and it almost seems to glow blue inside of the cave. There's something that's called the Blue Grotto in Capri, and it's one of the most famous examples of this. The light enters through an underwater opening. The red absorbed, we learned that already, by the columns of water, and the blue remains, illuminates the whole cave, and the walls and everything around it have that really amazing blue. It's just what the water does when the light happens and when you have darkness surrounding the area. Now, we talked about it before that when we talked about feathers, and we talked before, like I said, we talked about feathers, that when we have cardinals are actually red. Blue jays aren't really blue. Instead, the bird colors don't come from the pigment, the melanin that's formed inside of the feathers. Instead, blue jays have no pigment at all, And then if you took a blue jay feather and on the ground, you would probably see it looks very gray. The feather barbules inside of the feathers have tiny branches in them. They contain nanostructures, essentially, microscopic arrays with air pockets, and that protein scatters the blue wavelengths and absorbs the red and the orange, so you don't see that anymore, and only the blue bounces back towards your eyes. So scientists call this structural color as compared to pigment color. And so if you look at a blue jay's feather at the right angle, the right backlighting, the blue will disappear. The pigments will show and if you pick up a blue jay feather or you're close to a blue jay, if you look at it at the right angle, the blue disappears entirely. If you had pigment color, like the cardinal that's red, the feather would look red all the time. So that's kind of how it all kind of ties together. The iridescent throats of patches of a hummingbird, the wings of some dragonflies, that has to do with the selective absorption of long wavelengths, preferring to scatter the shorter ones. It's the same physics as the ocean itself, the glaciers that we just talked about, the same physics as the sky itself. So the universe just basically has that set of rules when it comes to light, and it plays around by those rules everywhere you look. So next time you go out looking at the water, any water, you're looking at a spectrometer of some sort. It is actively filtering the sunlight of every bit of sun that hits it every moment it exists. It absorbs some wavelengths, it scatters other ones, it reflects the sky, it's responding to what's beneath the lake or the water, and it's also responding to what lives in the water, what kind of microbes and algae and bacteria. The color you see is real information about the depth, the clarity, the particle content, the biology living in it, and the angle of the light itself. So if you're looking at a lake, try to think about it. What is actually causing this water to look like this particular piece? And once you start seeing light and you start being able to analyze it, you won't stop. This is what makes it so amazing that you'll be able to look around and start analyzing the water around you. All right, everyone, thanks so much. I appreciate you being out there, and I appreciate you listening to this little series on color and why things have color that is outside the pigment of whatever it is. You can email me at jill@startwithsmallsteps.com. You can put a comment right here. I'd love to hear from you. Thanks so much and have a great day.